Sorry about that. There was my screensaver turned on, which was a little bit confusing. Anyway, so the point here is that this type of experiment produces outcomes where I have two different real numbers that represent the x and y coordinates. So just the sample space there is also infinite, is also continuous, but in this case is two-dimensional. And that can occur. And we can have even more esoteric examples, so I won't write anything on the board for this, but you could imagine your experiment as being at 12 o'clock on noon, turn into a randomly chosen radio station in the Portland area and record 15 seconds of audio signal. And you can think of those 15 seconds of audio signal as recorded. If you sample at, I don't know, 20,000 hertz or something like that, that would be 20,000 times 15 sample values. So you could have your sample space be the space of all 15-second audio recordings, which you can associate with a set of real numbers that's like 15 times whatever your sampling rate is. So that's just to say that the structure of the sample space can potentially be very, very large. So maybe with that example you might ask a question like, what's the chance that among those 15 seconds that a song is playing, or a part of a commercial was playing, or part of a news program was playing, for example. So that's the notion of sample space, set of all possible outcomes for a particular experiment. So finally, I should note that this notion of the use of the word experiment has nothing to do with the normal notion in science of something that you do in order to answer a particular question about science. I mean, rolling the dice, we're not testing any scientific theory or anything like that. But in this context, I can call that an experiment because it's just a random process that I can repeat. Okay, so now I'm going to talk exactly about what I mean by an event. So an event is not defined to just be one of the outcomes. Rather, an event is defined to be, by an event, I mean a subset of the sample space. Or, if you want to think of it this way, you can also think of it as a set of outcomes. So, this can be a little bit confusing at first, because it's easy to think that, well, if an outcome is something that happens from the experiment, then that should be an event. So events should be things that can happen from the experiment. Just the way that we use this in probability is a little bit more broad. We don't think of an event as just being a single sample outcome. An event is allowed to be a collection of outcomes. So for instance, let's focus on rolling two dice. So we described the sample space for this as we can think of it as the set of all ordered pairs of numbers of 1 through 6. So I'll just put that on the board again. 1, 1, 1, 2, up to 1, 6, and then 2, 1, up to 2, 6, and this is going to go down to 6, 1. 6, 2, up to 6, 6. So that's our sample space. Now, events for this experiment are going to be subsets of that. So let me kind of give you a couple of examples of events. So by convention, we often refer use capital letters to refer to events. So I can say one event is the sum of the dice is 4. So this is an English language description of the event, but the event is a subset of these, so I can also describe it by explicitly listing them. So I could list A is going to consist of all of the outcomes of the experiment that are consistent with this criterion. So how can you roll two numbers to add up to 4? Charlie? Oh, that's right. So I could have 1, 3 would be one way of getting 4. But it's not the only way. Of course, I can roll a pair of 2s, and I can roll 3 with the first die and 1 with the second die. So this is what I mean by the set of outcomes that correspond to this event. Okay, so if I roll a die, I can ask, did event A occur? Well, no. In this case, I rolled a 1 and a 5, so event A did not occur. But if I had rolled a 1 and a 3, then event A would have occurred. So event A occurs if any of the outcomes in A are produced by that particular repetition of the experiment. So I can have another example is let B be we roll doubles. So if you play Monopoly or many different dice games, this is an event that has special significance there. I'm just seeing that I'm not sure you can read that easily. I have to remind myself to write bigger. So let B be rolling doubles. So I can also write B explicitly as a list, and it's just this. Let me choose a slightly more complicated one. Another event would be the number on the first die evenly divides the number on the second die. Okay, so if we think about what of these outcomes are consistent with this event or are contained in that event, we can list them. So we have 1 for the first is going to divide into any number evenly. So 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6 are all in that event. But if I roll 2 and then a 2, that's also in that event. If I roll 2, 4, that's in the event. 2, 6 is also in the event. And then 3, 3 is in the event. And 3, 6 is in the event. So if you think about it carefully, these are the only possibilities that are consistent with this event, that the first number on the first die evenly divides the number on the second die. Okay, so a little bit more notation. When we're dealing with sets and subsets, one notation is the following. If I write this, where I write the set and then I write these two things here that looks like an absolute value sign, this is the cardinality of A. It just means the number of elements in that set. So if we're talking about discrete sets, it's often helpful to explicitly count how many elements are in that set. So what's the cardinality of A for these examples? Well, it's just the number of elements in that event. So there's 1, 2, 3 different elements in that event. So the cardinality of A is 3. Similarly, the cardinality of B here is 6. And the cardinality of C is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So in a little bit, we'll see how we can often use the cardinality of sets to directly to determine the probabilities of those events occurring. Okay. So next thing we're going to talk about is set theory, notions of union, intersection, and complements. So this is the point in the class where if I were with you in person, I would say, how many of you have seen set theory before? And if you're all have seen it before, we just move on. Charlie, have you seen it before? Sadly, Charlie's just a squirrel, not even a real squirrel, just a stuffed one. So she hasn't seen this before, so I'm gonna cover it for her benefit. Okay. So events are sets, which is just like collections of outcomes. So we can take unions, intersections, and complements of these. So I'm going to leave this on the board here and work over on that side so that I can use those particular events as examples. Okay, so in general, if we have this is we're going to use this in probability theory, but it's also very widely used elsewhere in mathematics. If we have any two sets, we can define the operations of union and intersection. So if A and B are sets, then I'm going to introduce the following notation. If I think of A, and I write the letter U, B, this is an operation where we take A, so-called A union B, this is a new set that contains all of the elements of A and all of the elements of B. So if I think about these particular examples over here, if I have A union B, this is going to be everything that's in here, also everything that's in here. So it doesn't really matter how we order them, but I can write all of the doubles, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. And then we're also including the elements of A. So 1, 3. I wouldn't write 2, 2 because it's already been written in there. 3, 1. So that's the set that is the union. So it consists of everything that's either in A or B. Okay, so A intersection B, here we write with the U that's upside down, this refers to the intersection. this is the set containing elements that are in A and B. Okay, so this is basically the overlap. So think the elements that are both in A and in B. So if we go over here, A intersection B equals, well, what we're looking for rolls of dice that are both doubles and add up to 4. So if you think about it that way, you realize that it's 2, 2. Or if you just look at these lists and say what outcome is in this set and also in this set, it's 2, 2. Okay. So in this case, these two sets have an intersection that consists of just a single element. All right, the other operation I'm going to define is the complement. So the complement is going to be the set of things that are not in a given set. So I'm going to erase this now. So I'm going to denote the complement by writing the little c in superscript. So this is the outcomes, set of outcomes that are not in A. Okay. So now here's a sort of interesting or important point. A complement is the set of all things that are not in A, but it's always relative to the sample space of the experiment that we're talking about. So if I had my set B, which was doubles, and I said B complement, this would be all ordered pairs of numbers that are not doubles, or ordered pairs of numbers 1 through 6 that are not doubles. So B complement would be that. But it's relative to the sample set that we're talking about. So B complement does not include ham sandwich. Even though ham sandwich is not in B, it doesn't mean it's in B complement because ham sandwich is not in the sample space of things we're talking about originally. It's just a minor semantic point. Okay. So linguistically, there's an important interpretation of the operations of union, intersection, or complement. So linguistically, A union B means A or B occurs. So in my previous set here, I had A to be the set of numbers that add up to 4, and I had B to be the set of rolls that are doubles. And A union B says that event occurs if I roll the dice and I get either a double or a throw that adds up to 4. So here, I roll the throw that adds up to 4. So A union B occurred. I'll roll again. Okay, so this is 5 and 2. It's not a double, and it doesn't add up to 4. So A union B did not occur. Similarly, A intersection B means A and B occurs. So if an outcome is produced and A happens, which means that the outcome was in A, and B happens, which means the outcome was in B, then A intersection B happens because A happened and B happened. And then if I have A complement, this is linguistically equivalent to saying A does not occur. Okay, so for my sets here, B was the set of doubles. So if I make a roll, and I got a 6 and a 3, so B complement occurred because a double did not occur. All right. Finally, we should note, if we're talking about intersections, it's possible for sets to have no elements in common. And in that case, for instance, if I had C was the sets 1, 2, 3, and D was 4, 5, 6, then C intersection D is has no elements, so we write it this way. This is the notation for the so-called empty set. Okay, so don't get confused by that. You can have this. It's possible that this this set will contain no elements, in which case you call it the empty set, which we denote by the 0 with a line through it. So we also have this situation also has a couple of other names that we'll see. In this case, we can say that C and D are disjoint, which means they have no outcomes in common. We can also say C and D are mutually exclusive. Which is basically means if C happens, then D cannot happen, or if D happens, then C cannot happen. So these are just saying C and D are disjoint, C and D are mutually exclusive, C and D have empty intersections, C intersect D is the empty set, all mean the same thing.